First of all, I'd like to thank the organizers for having me here. And I was asked to talk, in fact, about techniques to search for continuous gravitational waves. And so this is mostly what I'm going to try and do. Well, what does this mean, first of all? We all know that LIGO has detected a number of in spirals leading to merge of compact objects in binaries. My personal favorite, perhaps I'm a nostalgic type, is the first one, GW 150914. Here, give and take is the time scale that is common to most systems. I said give and take, it's less than a second. But from my perspective, they're all short signals. And short compared to the nearly pure tone that would come in gravitational waves from a rotating compact object, a rotating neutron star. So the types of signals that I'm looking for are the ones that are very, very weak, but they're there all the time. So very different from the very exciting and detected, actually, big splashes that come from the mergers of black holes and neutron stars. So there's a variety of situations and mechanisms thereby which a compact object, let's say a neutron star for simplicity, could have a quadrupole moment that, due to its rotation, would generate continuous gravitational waves. And the simplest scenario that I'm going to refer to is that where the neutron star is deformed. It's got like a bump. Okay? And this is typically described by this quantity here, that's the ellipticity. And then the intrinsic gravitational wave that arrives at a distance d from the object is directly proportional to this ellipticity, to this deformation, and also scales with the square of the gravitational wave frequency. In this particular case, also, the gravitational wave frequency is expected to be twice the rotation frequency of the star. Now, the problem with this type of signal is that how large this is, which ultimately sets our chances of actually being able to detect it, is very uncertain and ranges in values from 10 to the minus 3 even to values which can be as low as you like. Let's say a realistically lowest value ranges in the orders of 10 to the minus 12. So there's many orders of magnitude of uncertainty here. Now, if we wanted to look for emission from these objects, there's an obvious place to start from, which are the known pulsars. And here you've already seen this diagram. It plots the period and period derivative for the population of known objects, more than 2,000 of them. And of these, a certain fraction have rotation frequencies that then would put them at twice the rotation frequency in the high sensitivity band of LIGO. And there are ones here, the ones to the left of this green vertical bar. So what do we do? Well, under the assumption that the phase of the gravitational wave signal is locked to that of the rotation of the object, seems very reasonable. The gravitational wave signal is completely predictable. It's just nearly a sinusoid at twice the rotation frequency of the object, and nearly because actually we observed that these pulsars spin down, so it won't be completely monochromatic. You'll just have a little spin down. And so we know exactly what wave shape to target, and we do that. And we do that, and we search it with the most sensitive technique which we have, which are just coherent techniques using the whole observation time. And these are what we would call, in the language of the compact binary searches, single template searches, because we know exactly what the wave shape is that we are expecting. And so they're the most sensitive. And here are the results from the latest published search, which was on O1 data. And the only thing I'd like you to concentrate on are the blue markers. So these are our measured upper limits, because unfortunately we haven't detected anything. And so not having detected anything, what we can we can do is set upper limits on the gravitational wave amplitude of the detector, which is consistent with the null result. And these are these stars, blue stars that you see here. And it's interesting to compare them with the spin-down amplitude, which are the triangles. What is the spin-down amplitude? Well, we know for each of these objects what its spin-down is. So we know how slowly it is losing energy, okay, kinetic rotational energy. So under the assumption that all that lost kinetic energy all goes into gravitational wave emission, knowing the distance of each of these sources, we can derive what the H0 would be that would sustain such emission. And this is what these with little triangles are. So for every one of our measurements, there is a corresponding triangles. And our measurements are informative only if the triangle is above the star. Means that our measurements are actually more constraining. And the objects for which around the star there is a little circle are the handful of objects for which, in fact, our upper limits are more constraining than these indirect spin-down upper limits. And there's a handful of objects here. Now, this might appear good news, but it is sort of. Because here I recall the first and one of the very few equations I'm going to show, which was the way that the ellipticity of the objects connects to the amplitude. So once I have upper limits on H0, on this amplitude, knowing the distance of each of these sources, I can recast them on upper limits on the deformation ellipticity of the object. And this is actually just what is done here with the same sort of markings. And so you can see here that the object for which we beat the spin-down limit are actually also the objects, though, that have the highest spin-down ellipticity. So unfortunate, these are not very interesting value per se of the ellipticity that we're constraining. On the other hand, there are interesting upper limits on the ellipticities that are, in the 10 to the minus 8 regions, typically for objects at higher frequencies. This is obvious looking at this formula. And nearby objects, but for these, the spin-down limit is even an order of magnitude lower. So that's the story for the known objects. So is there hope? Well, I would say so, because we know that in the galaxy of these 2,000 plus objects that we see, is not all there's there. There should be orders of magnitude undiscovered, not known objects. And there might be just one that is close enough and deformed enough and spinning in the right range that we might actually be able to detect it. Something I would like to point out, and possibly it's one of the messages that would be worthwhile to take home from this talk, is that as we have to search for more waveforms because we don't know the signal parameters, intrinsically the sensitivity of our searches decreases. So the minimum detectable signal increases. And this is why, and this is because when you do a search and you try many, many waveforms, at the end of the day, you have simply values of the detection statistic that tell you, how likely is it that you have a signal rather than noise. And these are random variables, are realizations of whatever random variable your detection statistic happens to be. And if you've done many trials, tried many waveforms, it is just purely by chance, the loudest, the most significant of that is going to be higher the more trials you do. That's the trials factor. So when you do many, many trials, you have basically to fight with noise fluctuations that are higher. So if you want to keep the significance of your finding constant, basically you require the signal to be higher. It has to fight against higher fluctuations. And so going from the non-pulsar searches, where you basically know everything, to searches for objects for whom you might know only the position, you don't know the frequency, you don't know the spin down, to all sky searches where you actually don't even know the position, And then even worse, if you do that for pulsars in binaries, where additionally you also have the orbital parameters, your search sensitivity decreases. So as I was saying, though, before, the fact that I think the prospects, I shouldn't say this because I'm being recorded, that it's really nice. It would be, I think it's very promising. It might be that the first detection is going to be by an object that we don't see a priori. It's just bumpy enough or close enough that we might be able to see it. The downside is that we're going to pay for this in terms of the sensitivity. Now, what's the challenge with this? So the signals are weak. The H0, is 10 to the minus 25 or so. And we don't know where it may be coming from. So to dig it out of the noise, like we do for the non-pulsars, we want to combine all the data coherently for very long observation times. But we are sitting on a detector that is orbiting around the sun. And so what happens is that the signal that we get has a Doppler modulation that encodes actually the information of where it is in the sky. And pretty much like in aperture synthesis from a telescope, when we get a year of data from our detector, it's a bit like the resolution in the sky. It's a bit like that of a set of gravitational wave detectors making observations at one time around this solar sort of observation dish. Okay? So we have, for long observation times, which are months, close to a year, the sub-arc second resolution at, say, a kilohertz that is typical of radio telescopes. So unlike what happens for CBC signals, if we actually do make a detection, we'll have incredibly good pointing accuracy. We'll be able to tell our astronomer friends exactly where to point the telescopes and see if they see something. But this also means that when we do these blind surveys, we quickly, for big broadband searches like a kilohertz, we quickly have to survey something like 10 to the 17 different waveforms. And so the first challenge with that, apart from the loss of sensitivity just due to this enormous trials factor that we have, is that they're computationally, with the brute force approach of just integrating coherently over months, they're not doable. So we've developed other techniques where we basically chop the data in segments, do the coherent analysis, which is the most expensive, over the shorter segments. We make them basically as long as we can so that it's still computationally feasible. And then we combine the results from the different segments incoherently. And this allows us to keep the computational cost under control at the expense of some sensitivity, obviously. And now here, how does the SNR scale? Just want to say that at a given sort of noise, with given noise, it basically goes like the square root of the coherent integration time, the coherent observation time, and with basically the fourth root of the number of segments. And basically, the searches are divided in searches where we make this very short, in fact, short enough that we don't even need to do a specific search for every segment. A Fourier transform is enough. Why is that? Because the Doppler modulation during the observation time is such that the signal is all still in a bin. The instantaneous frequency during, let's say, half an hour doesn't move by more than a frequency bin associated with half an hour, which is of the order 10 to the minus 4 seconds. And then we combine all these incoherently, and we have many. And of course, the sensitivity is much less than if instead we had segments of, say, 10 days, for which, though, we have to do a lot of searches, searching many positions in the sky, because with that type of resolution, we can appreciate that many sky positions. Another thing I want to point out is that unlike what happens for searches in spiral signals, since these are very expensive, we can't do the analysis quickly once, then wait for the data to be characterized, finally calibrate it, clean, and redo it. It's just too terribly expensive. So we basically have to wait until we have the final data set, and then we process it. Another thing is that if we look at this here, in order to do this combination, we need to have all the segments. It's just too many positions in the sky, too many intermediate data products to store as we wait for more data to come in. So typically, continuous wave searches lag in results about one run behind all the other results. We just have to wait to have all the data in the can before we can start. And there are basically two different types of surveys that we can do. One is very broad, fast turnaround of results, and robust. Robust in the sense that the coherent time baselines that we use for the segments are very short. So if there's any deviations of the actual signal from a perfectly coherent signal, these do not impact the sensitivity very much, because the basic timescale for sensitivity is shorter. And then there are these other searches, which instead the deepest that we can do. They're the ones where we say, well, let's suppose that our signal is indeed phase coherent over many months. Let's concentrate our computing power to do the very best that we can. And these are our deep surveys. And these are carried out on different computational facilities. The fast turnaround searches are still computationally intensive. They run for weeks on our LVC clusters. This is the one we have in Hanover. And these ones are ones that run on volunteer computing project, Einstein at Home. This is petaflops of computing power sustained 24/7. And these are searches that last months on this infrastructure. And actually, when we do the deepest searches, we don't just do one semi-coherent search. We use a whole cascade of them. And we move in the direction of fewer and longer segments at each stage of the cascade. You have to think about it as a zooming procedure. We start with 10 to the 17 templates. And at each stage, we require candidates to pass to the next stage to be above a certain significance level. And so there's more and more noise rejected, and the significance, though, of a putative candidate, since the time baseline of the coherent segments increases, our searches become more sensitive, would increase at every stage. These are actually very complex methods, and it took us a good portion of 2 decades to develop them. So far, we haven't actually seen anything. So far, no candidate has actually survived the whole hierarchy of stages. And would be an interesting question to ask, would we be able to actually claim a confident detection just after one of these hierarchies? But I'm not going to answer this now. So we haven't seen anything so far. And so what we do typically is we set upper limits as a function of frequency on the gravitational wave amplitude. So these have to be interpreted like this. You don't see them, but there's a discretization in about 1 hertz of half hertz bins. And what these means is the following. There was no source emitting gravitational waves that would have produced an H0 at the level shown here. So for example, here would be just over 3.2 times 10 to the minus 25 in the range between 200 and 201 hertz, and so on. And here you see the results from a broad, fast turnaround search. And here, this was a very deep search done on Einstein at Home. And here's a zoom, targeting low-frequency objects. And you can see that this improves with respect to the fast turnaround search, which wasn't that fast turnaround, actually, by about a factor of 2. And that might not seem a lot to you, but actually, 2 cubed is 8. That means potentially a volume which is 8 times bigger. So we think it's actually worth the trouble of trying to do these deepest searches. And these are the the papers. So how does this translate into ellipticity upper limits? Now, these are surveys. I'm not targeting specific objects, so I don't know the distance. And so if I have to give upper limits on the ellipticity as a function of the frequency, they'll be parameterized by an assumed distance. And so we see here that our reach, first of all, is absolutely galactic. We are not going to be seeing anything that's outside of the galaxy. And let's take 100 parsecs. Well, at 2 kilohertz, we're probing ellipticities that are, around a few 10 to the minus 8. These are actually interesting upper limits. And of course, linearly scaling with the distance if we want to make statements about there not being objects with ellipticities, let's say, greater, let's take, for example, a kilohertz, greater than 10 to the minus 7 for frequencies above 820 hertz within 100 parsec. That's the type of statement that we can make based on this. So intermediate between the searches where we target objects for which we know everything, the crab, we know frequency, spin down, its position, we know everything about it, and objects where we do all sky surveys where it's a blind survey. It's targeting objects for which we know the positions, but actually we don't know the frequency and frequency derivatives. For example, Cassiopeia A. These, typically we choose young objects because these are the ones that we'd expect would be emitting more, higher possible frequency, spin down, so a larger reservoir of energy, part of which could perhaps be going into gravitational waves. Okay, this is our so the most recent existing upper limit on the ellipticity of a subchart object is given here. This was a deep search carried out on open data, in fact. And it put upper limits in a band that was between about 100 and 1,000 hertz. And the corresponding ellipticity upper limit is this red curve here that touches at a kilohertz about 2 times 10 to the minus 5. These are higher ellipticity numbers because Cas is much further than 100 parsecs. Okay, so, but we could do, because we actually had only one sky position to survey a quite sensitive search. Generally speaking, though, we have to make decisions. Which targets do we pick? Do we go for the youngest, which in principle you would expect a higher spin down, so higher possible emission, the closest? What frequency range, what spin down range? Do we trade breadth for depth? Because forget not, we are operating at fixed computing budget. And how do we set up the searches? That's another question. So we are developing optimization schemes to make these decisions rationally and not just based on hand-waving arguments, because there is a non-trivial interplay between all these quantities and our search algorithms and the sensitivity that you can get out of them. So in O1, we have run a search that targeted 3 objects, Vila Junior, Cassé, and G347.3, each one with a different search setup, with the prescription given by an optimization scheme that is supposed to maximize detection probability over all these choices that we have to make. So these were the target that came out, and this was the parameter space that the optimization scheme prescribed to search. This is a search that ran on Einstein at home. It ran for 6 months, and we are now post-processing the results of it. And it's a very broad frequency search. It goes to 1.5 kilohertz. This is what we expect in terms of sensitivity if we don't detect anything. And for the Cassé is this object up here, and we expect upper limits on H0 sensitivity. Let me not say we expect upper limits. We expect a sensitivity which is at least 2 times better than the one of the result that I showed you. So, prospects. As I said before, with all due respect to our CBC colleagues who've done a fantastic job, I do think that even though our signal is that simple, doesn't require the complexities of the modeling that the CBC signals do, the searches per se, given how computationally intensive they are actually among the most complex that we do. It's really a multi-layer pipeline. And just to give you an idea, we're doing the best that we can. Not completely quite there, because there is about a factor of 10 in sensitivity between the targeted searches and our blind surveys. And so one way to ask, is this really the best that we can do? You should ask how much you can't really do anything about, which is the trials factor. And that's about a factor of 5, 6. So actually, since we're at a factor of 10 worse, I think there's still room for some improvement. And for broadening the scope of the searches, for example, relaxing the assumption of the signals, but also looking at searches that might target different emission than the vanilla type of emission that we've looked at. Even perhaps there's predictions for emissions from axion clouds around black holes. Those would be continuous wave signals. Perhaps we might detect that as the first continuous wave detection. Is the continuous signal the next new thing that LIGO is going to detect? I wish I could say so, but actually, given the huge variability in predictions on these deformation parameters, I don't know. But we are probing interesting ellipticity values, so certainly very respectable and respectable ranges. And especially in conjunction with electromagnetic observations, I think we could, if we did make a detection, we could gain some insight in what's happening in the star and possibly glimpse in this invisible population of neutron stars. So I'm going to close here with a hopeful, kind, nature has been kind to us so far. I hope it continues, and I hope soon I'll be able to tell you something about a continuous wave signal. Thanks.
Apologies if I missed this in your slides. So in terms of if you end up identifying another previously unidentified continuous source, what kind of sky localizations are you able to provide?
Yeah.
And the follow-up question is, I realize there are MOUs in place to work with observers on the time domain, the CBCs and stuff. Is there a similar astronomers working with you to follow up continuous sources?
Mm-hmm. Well, so as I explained before, the time of accuracy that we would have is sub-second accuracy, and that just comes from the fact that we're basically doing aperture synthesis. So there's no more than that. And we do see that. If you see any of our papers where we give results from deep searches, we always provide, even though there's nothing significant, information about our top 10 out of the 10 to the 17 outliers. And we give the uncertainties associated with them, actually tested with Monte Carlo simulations of our detection efficiencies, running them through our pipeline, and we confirm the types of resolutions in the sky that we'd expect. This is number one. Number two, do we have plans with astronomers? So we have, first of all, there isn't a sense of urgency to try and prepare well in advance because there'll be a clock ticking. We don't get the results well after the run is finished, and the signal is not going to go away. So there hasn't been that much work in that respect. However, we are starting to think about what we would do if we really had an interesting candidate. Exploiting, first of all, sort of archival data. Apparently, there's a lot of archival data that hasn't been looked at very carefully, and with a specific with a specific candidate from our observations to look for, that'd be an interesting thing to do. And we're trying to start looking, for example, at what the false alarms associated with such a study would be.
Maria Alessandra, if you are looking for SCO-X1, what is your limit? How long can you integrate at the moment with these coherent searches?
Yeah, so, yeah. It's a very broad parameter space search, as you know. And currently, we are using cross-correlation methods.
So that's the best, and you can't do any better with
well,
coherent
I mean, we can increase the coherent, the sort of T-lag of these, but then we have to start correcting. And if we start correcting for the Doppler modulation, that means it becomes very expensive. And this is why we are improving on the last cross-correlation method by actually trying to speed up that computation. We use now resampling rather than demodulation in the frequency domain. And in the ongoing SCO-X1 mock data challenge, we'll benchmark that. Right now, I mean, up to this improvement, we were using coherent times of the order of an hour, so not very much.
This is related, but not directly connected with what you said, but people have made estimates of the magnitudes of glitches in various neutron stars. And the glitch would give you a signature that would be like this, it would be transient, but it would be similar frequency. It wouldn't be changing too much. Have you explored this as well? I know that you have to have time coincidence, and that glitches don't happen that often, but it might be a signature that could be detected with some art and some luck.
Yeah. So in the searches for non-pulsars, glitches are a headache in the sense that they interrupt the complete, phase coherent integration. So we actually have to bunch the data in different stretches, interglitch, and then combine it. In terms of, and in all sky surveys, we're not targeting any specific object, right? So again, a glitch is a bad thing simply because it might impact our detection efficiency because we operate under the assumption it would impact our detection efficiency that at least over, let's say, 200 hours, the signal is phase coherent. It could provide some useful information if we had a very significant candidate, we looked at the EM data, we found something, looking at it even more, we identified a glitch, and then we could cross-correlate it with our gravitational wave observations. There we would definitely see a glitch because it would, if it were big enough at least, we would see a loss in our detection efficiency, in the way that the SNR accumulates. But at the present time, a glitch is an evil thing that is going to makes it harder for us to detect.
Nevertheless, it would be nice to, if you were looking at a pulsar, the Vela pulsar, for example, it's period, and you just get lucky. You see a glitch, you've been monitoring,
sure,
etc.
Yeah.
So it would be nice to make an estimate of what the magnitude of the gravitational wave signature should be under those circumstances. Maybe this has already been done, but it would be nice to, because you were talking about ellipticities of 10 to the minus 4, 10 to the minus 12.
So we're actually doing something perhaps which is the closest to what you're saying. The greatest glitcher is J0537. It glitches a lot. And there have been studies, recent studies by Win Ho, Niels Andersen, and collaborators that having analyzed something like a decade of timing data, they've realized that if you, after a glitch, if you take the timing data not immediately after the glitch, but something like 50 days or so after that big glitch, and then estimate the breaking index until the next glitch, The breaking indices that they get are around 7, which is suggestive of R mode emission. Now, they themselves call this sort of speculative. However, we are looking in the possibility. Unfortunately, for O1 and O2, there was no telescope that observed systematically J0537 that can give us information about when the glitch happened. So what we're trying to do is to do a search for transient emission with varying start times and various duration, trying to see if we can catch that period of high R mode emission. Although I must say that at the sensitivities of O1 and even O2, unfortunately, for shorter observation times like the ones that we are looking at, we wouldn't be able to even reach in sensitivity the spin down limit. So,
Thank you.
A question for you. And that's signal to noise formula you showed for incoherent averaging. It was the n to the 1/4 power.
yes.
Which is a standard formula.
Yeah.
So, but you have situations where you do much worse than that. What is the reason?
Yes. Well, it's that our methods are not always able to gather all the power that in principle is there. And that's one of the things that we are actually, in fact, fixing.
Okay. So let's thank Maria Alessandra again.